Hi everyone, my name is Prateek Gupta. I am a second year PhD student at Purdue University and I am pursuing a PhD under the guidance of Dr. Doresomi Ramakrishna. Today I wanted to discuss with you the cybernetic modeling of the L-Arginine pathway in macrophages during wound healing. So chronic wounds, they fail to heal properly due to a combination of factors including underlying illnesses like diabetes, advanced age, repeated trauma, and sometimes genetic predispositions. Among these, dysregulation of the immune system and specifically macrophage behavior plays a central role. Diabetic foot ulcers alone account for over 80% of lower limb amputations, with venous leg ulcers costing the US healthcare system over $14 billion annually. These statistics underscore the critical need for mechanistic understanding and therapeutic innovation. It is well established that the macrophage cell is a central regulator of inflammation and wound repair. Under normal circumstances, macrophages undergo a phenotypic transition from the pro-inflammatory M1 state to the pro-resolution M2 state. However, in chronic wounds, this transition is often incomplete or dysfunctional, leading to prolonged inflammation, fibrosis, or even pathological scarring such as keloids. Our central hypothesis here is that this phenotypic transition is governed by a metabolic switch within the L-Arginine pathway, regulated by a competitive interaction between the transcription factors STAT1 and STAT6. This regulatory mechanism is proposed to serve as a master control for macrophage polarization and consequently for the wound healing trajectory. To investigate this, we developed a cybernetic model, a mathematical framework that mimics how cells allocate their metabolic resources to achieve specific physiological goals. In our case, these goals are the optimal production of nitric oxide in the M1 state and L-ornithine in the M2 state, the two key metabolites indicative of macrophage function. So these cybernetic models find their origin in optimal control theory and theoretical ecology. They are based on the idea that cells utilize their resources in an optimal manner to achieve an end goal. An optimization problem can be easily set up and solved using the method of Lagrange multipliers to get the mathematical form of the control variables u and v, where u signifies fractional resource allocation for enzyme synthesis and the variable v signifies the level of enzyme activity. Once integrated into the ODEs, our model comprises of 5 ordinary differential equations along with 12 parameters. These parameters were calibrated using a genetic algorithm, allowing us to fit observed metabolic behaviors under varying conditions. Besides fitting our model to the experimental data, we also wanted to compare our cybernetic approach with the traditional Michaelis-Menten model, which we refer here as the classic model. So as you can see here, the fits given by the Michaelis-Menten kinetics are really bad. It's not even capturing the basic trend of the experimental data. Whereas our cybernetic model, which has regulation incorporated into it, is giving much better fits. Also, we have here a plot of U1 versus U2 and V1 versus V2. So initially, the wound site is dominated by the M1 macrophages, which is why all the flux is directed through the first branch. And that is why the variable V1 is initially higher. Then somewhere around day 1, the M1 cells, they polarize into the M2 cells, and the flux is readjusted towards the second branch, and the variable V2 becomes higher. So clearly this switch in the pathway is depicted by our cybernetic model. What's particularly powerful about this approach is that it abstracts the cell's behavior as a resource allocation problem, governed not just by static pathways, but by a decision-making logic. This allows us to simulate and predict switch-like behavior in response to changes in cytokine signaling or metabolic load. Our framework also sets the stage for integration with single-cell RNA-seq data. While macrophage states are often simplified into the M1, M2 binary states, recent transcriptomic analysis reveals a spectrum of activation states. A cybernetic model provides a natural way to interpolate these intermediate phenotypes. Looking ahead, we aim to extend this model to multicellular wound microenvironments, including interactions with fibroblasts, natural killer cells, and T cells. Ultimately, we envision this framework as a stepping stone towards rational design of wound therapeutics. Thank you.